Welcome to my YouTube channel. In this video, we are going to learn how to use the solution series technique to solve differential equation. And this differential equation we want to look at, it's a simple first order differential equation. It has this form: dy dx plus ky equal to 0. Now to solve this problem, we assume the solution y has a form of y equal to summation of an x raised by r plus n, where this r is a constant, n runs from 0 to infinity. Okay, so the idea is to look for the constants a0, a1, a2, and also this r. Once we can find those constants a0 to infinity, a0 to a infinity, then r, then we'll substitute it back into this equation, and that's all. If we expand this equation, it will give us something of this form. So this one is a short form of this one. So we can see a0, a1, a2, a3, xr plus 0, x raised by r plus 1, x raised by r plus 2, and down to infinity. Right, so what we need to do is to differentiate this one with respect to x, and also leave this one and substitute both into this one. So when you differentiate this one with respect to x once, we get an expression of this form. Okay, we can see r plus n will come back because we differentiate with respect to x, and this gives us this expression. So if we substitute this expression and this expression into this, we should have something of this form, which is summation of this first one, which is exactly this. Then we have k, which is this, multiplied by this one here. So we have this. Now if you look at this equation, right, there's what we call the initial equation. And for us to get the initial equation, we consider this expression here, an r plus n x r plus n. So let's check what we need to do to these parts to get the initial equation. So this is the parts that we are still talking about. To get the initial equation, we replace n with 0, and in doing so, anywhere we see n in this expression, we replace with 0, and now we get this reduces to these parts. So from these parts, we notice that if we expound our original y, this x raised by r minus 1 cannot be found within that part. So for instance, let's assume our y has this form, a naught x r plus this. So you notice that we have x raised by r plus 0, x raised by r plus 1, down to infinity. You can never find this x raised by r minus 1 in this expression. So what that implies is that therefore the coefficients of this xr, which is a naught r, should be equal to 0 if this one does not exist in this expression. That leads to r a naught equal to 0. So this is the initial equation. Now that we have this, because our a naught, it's a very important parameter that must be determined, we can conclude that r must be equal to 0. A naught can never be equal to 0. So in this case, we make r equal to 0, which leads to r equal to 0. And we move on to get the next expression. So we still come back to this original expression, right? We've been able to find that r equal to 0, which is this r. We have established that fact. So to get the a naught, a1, a2, a3, we need what we call the recurrent relation. To get the recurrent relation, we use the same expression, and we assume that this expression, there's something we need to do to this expression to make it look like this expression, x raised by r plus n minus 1, this. And what we can do to this to make it look like this is to replace n with n plus 1. So wherever we see n in this expression, we replace with n plus 1, and that leads to this expression. So if you now see an is now an plus 1, r plus n is now rn plus 1. If you replace n with n plus 1, you get rn. So you see these parts, they are exactly the same. Now the idea is to get the recurrent relation. We'll move on to the next part, which is this. You notice that this one is common to both sides, so we'll factorize it out. And we can eliminate this one so that it will become only this part equal to 0. And which is this part. From this part, we can take this one to this other side and it gives us this. And from this part, we can make an plus 1 the Soviet formula, and that gives us this expression. So from here, we can now see the connection between an and an plus 1. So this is a recurrent relation. What this means is that if I know this part, which is a0, I can now get my a1. If I get a2, I can get my a3. If I know my a4, I can get my a5. But mind you, remember that our r here is already equal to 0, which is this. So when you make that substitution of r equal to 0, it gives us this part. So if we move on, we can decide to say if here is 0, then here will be 1. And that gives us, so a1 is equal to minus k a0 all over 1, because this one is already 0. Okay, so we go ahead to get that of a2. Once we get the first 3 terms, I think that's okay. Then we'll now go and substitute back into our y expression. And these are a3, right? We substitute the value of a2 here, 2, wherever we see n, put 2. Remember here is n plus 1, so 2 plus 1 is 3, then minus k. But remember, what is our a2? This is our a2. a2 is this final expression. We'll replace with this one here, and it gives k3 a0 all over 3 factorial, because this one is 3 and 2 and so on and so forth. So finally, we bring out this final, these are our original expression of y. Now we already know our r to be what? 0, right? It's supposed to be 0 plus 1, 0 plus 0, which will give us 0. Our r is already 0, 0 plus 1, because it's going to give us this expression. Our r is already 0, 0 plus 2, 0 plus 3, down so on and so forth. Now that we know what a0 is, x0 1, and so on and so forth. So we can substitute these values and we get this. So our a1 is k a0 all over 1 factorial, then x1. Our a2 is k squared a0 all over 2 factorial x squared. a3 is minus. Then we come to this place, we factorize a0 out. Remember, x raised by 0 is 1, so if you factorize a0 out, we get this expression. And from this expression, we can see that this expression has a typical resemblance to one of these series, which is the exponential series, negative exponential series. So, and that gives us our final answer. So a0 is a0, then exponential, this part is exponential minus kx, and that's it. This is now the solution. Thank you for watching. Please like, share and subscribe to this YouTube channel.